Welcome! I am Teresa Tarbuck, Assistant Professor of Chemistry. In this video, we will look at how to calculate standard cell potentials and Gibbs free energy changes for batteries. A voltaic cell, also known as a galvanic cell, is an electrochemical cell that uses spontaneous redox reactions to generate electricity. It consists of two half cells. A half cell can be composed of an electrode, a metal strip, with a solution containing metal ions. Here is a zinc strip in a solution of zinc nitrate, which is the source of zinc ions. The other half cell is a silver strip with silver ion solution. The two half cells are linked together by a wire running from one electrode to the other. A salt bridge also connects the half cells so that each half cell can maintain a net charge of 0 as the electrons are transferred. The salt bridge is a vital component of any voltaic cell. Here we are using filter paper soaked in potassium nitrate. The overall standard cell potential must be positive for a reaction to happen. The element or compound with the larger reduction potential, greatest oxidizing agent, will require the electrons. In this case, the silver ion has the largest reduction potential, 0.799 volts. It will acquire the electrons at the cathode. If 1 molar concentrations of silver nitrate and zinc nitrate are used, the theoretical standard cell potential can be calculated from the listed reduction potentials. The silver ion is reduced to silver solid, gaining electrons. The half cell potential is 0.799 volts. The zinc is oxidized to zinc 2+, losing electrons. The half cell potential is positive 0.76 volts. The oxidation reaction runs in reverse of the reduction, so the sign on the potential is also reversed. Before adding the two half cell reactions, the charge must balance. If zinc is providing 2 electrons per mole, we need another mole of silver ions to acquire the 2 moles of electrons transferred. We multiply the silver reduction reaction by 2 and add the half reactions together. The cell potential is positive, 1.56 volts, and the reaction is spontaneous. Electrons always flow from the anode to the cathode, or from the oxidation half cell to the reduction half cell. Now let's write out the compact cell diagram and calculate the Gibbs free energy. A cell diagram is a representation of an electrochemical cell. To calculate the free energy, we need the number of moles of electrons transferred in a reaction, 2 moles of electrons, Faraday's constant, 96,500 coulombs per mole electron, and the standard cell potential, 1.56 volts. Multiplying these, the free energy is negative 301 kilojoules, and the reaction is spontaneous. Calculating the non-standard cell potential for solution concentrations greater or less than 1 molar requires us to use the simplified Nernst equation. Here is a half molar zinc ion solution and a 1/10 molar silver ion solution. The cell potential is the standard cell potential reduced by a constant factor, 0.592 times log Q, divided by the moles of electrons transferred. In this case, the moles transferred are 2. Here, Q represents the molar concentrations of the product ions over the reactant ions, raised to their stoichiometric coefficients. In this case, we would square the concentration of silver ions because 2 is the coefficient in the reaction equation. Simplifying, we come up with 1.54 volts for the non-standard cell potential. Thank you for joining me to learn how to calculate standard cell potentials and Gibbs free energy. To learn more chemistry, look for our other educational videos on a variety of topics.